This is NeuroCave Plus, an application for exploring synaptic plasticity. It has free-form exploration of connectome datasets through node link diagrams with various edge display and display settings, pre-computed topology transforms, and data-derived color encodings. It allows for exploration of synaptic plasticity with side-by-side views that can be used to compare sequential or distant simulation steps, and coordinate systems and color codes can be set to track the evolution of n-grams to achieve new steady states. Why NeuroCave? Well, NeuroCave Plus is built on top of it's an additional features. We built some additional features onto NeuroCave. NeuroCave was originally constructed to facilitate the comparison of structural connectomes using interactive web-based viewports for comparing brain connectomes as node link diagrams, color mapping features for highlighting brain anatomy and brain clusters, and with an optional VR mode. So the added features in NeuroCave Plus include, well, we scaled the system to allow for 50,000 nodes, because most connectomes from an MRI were only about 5,000 nodes, the most. And to do this, we had to change the dense matrix representation of the connection matrix to a sparse matrix. And we also accelerate even further by pre-processing the connection matrix into a JSON object, which could be loaded faster. It allows for switching time steps and different subject faster. The edge particle simulations were added to provide directionality to node connections, as regular MRIs, like for diffusion tensor weighted imaging and things like that, or only provide correlations but not a directional connectivity, whereas the simulation had a connectivity, directional connectivity of to and from synaptic firing rates. We also added a toggle button to change the visibility state of all the nodes and to distinguish any region from any other regions, what that helps with. And there's also an independent left, right, and box and sphere control, size control, scaling controls that help identify the stimulus and lesion nodes represented as boxes, and the regular nodes are represented as spheres, so you can control them independently in the left and right viewports. So this image shows simulation step 90,000 in the original burn-in data set simulation, where it started with no edges and allowed the edges to organically evolve over time. So after 90,000 steps, the U-map transformation shows the formation of a line attractor that signifies the first memory m-gram emergence. On the right, you see the anatomical coordinates in the color code of the left U-map grid. The grid U-map color coding is it assigns colors based on its the regions in the continuous manifold space. So any region in this manifold space is a patchwork colored, and these colors can be applied to the anatomical coordinates, so you can see which anatomical coordinates roughly map to which topological locations. In this view, it shows that the left is an isomap transform that shows the roughly octahedral null intrinsic topology of this simulation, and so the isomap view organizes the nodes into clusters of highly connected nodes, and they form this octahedral shape. The right shows the distribution of the nodes in their color code on the brain anatomy. It doesn't really have a very obvious distribution. They're kind of randomly scattered around, but it does show that they do in an anatomical space, but the connections do apparently organize into a set of structured nodes out of the topological space. A closer view into a heat map of the hub node that is shown here. When we apply a heat map to it based on the target calcium color code, we see that the central node has rich in yellow nodes and blue shades, which are high on the heat map levels, and has reduced numbers of red and orange nodes, which would be low on the heat map, showing that this is enriched in high calcium nodes, as expected for a hub node. 2 simulation steps. So this is simulation step 70,000 on the left and 60,000 on the right. It was enriched in blue nodes, and now it's enriched in step 60,000 and 70,000. It's enriched in red nodes, showing that it's cooling off. This shows an ensemble exploration. So the left is a lesion and the right is the stimulus, both at 50,000 milliseconds after induction. The color code shows the original boundaries are deformed after mapping. The formation of the line engram at the UMAP coordinates, and both stimulus and lesion simulations form line attractors after 50,000. The distant time step comparison of the same simulation, you see that before the steady state, there are relatively few edges. After the steady state is achieved, there are many edges, many more edges. But the overall topology seems to return back to this spheroid patchwork state. In this slide, we explore the evolution of the calcium network side by side with ISOMAP and UMAP side by side. So in step 50,000, it appears that there's a line attractor forming on the UMAP representation, and there's 1, 2, 3, 4, 5, 6 clusters shown in the ISOMAP. And by step 60,000 milliseconds, you see that the line attractor is starting to collapse back to its spheroid form, and there are 1, 2, 3, 4, 5, 6, 7 co-communicating clusters. So it seems that it finally found a 7th cluster in its organization, and it's starting to collapse into its steady state form. Thanks for watching.